Alright, now we're down to the heart of propositional logic, proofs. So we want to start looking at proving various propositions using all of this machinery that we've been developing over these past few lectures. So let me give you a definition. A theorem is a statement that can be shown to be true. So when someone states a theorem, what they are doing is they're making a statement that can somehow be shown to be true. If it can't be shown to be true, but it can't be shown to be false, it's a hypothesis. It's something that may be true. Throughout this, we're going to pick on a particular characteristic of numbers that we can use in various proofs, which is the notion of being an even or an odd number. So let me give you some definitions. An integer n is even if there exists some integer k such that n equals 2 times k. An integer n is odd if there exists some integer k such that n equals 2k plus 1. Okay, there exists a k. So for example, the number 4 can be written as 2 times 2. There exists a k, 2, such that n is equal to 2 times k, so 4 is even. The number 17 can be written as 2 times 8 plus 1. There exists an integer k, in this case k equals 8, such that n equals 2 times 8 plus 1, 2k plus 1, therefore 17 is odd. Okay, and we're going to use these as sort of a fodder for doing some proofs and showing different methods of proof. So the first method of proof is called a direct proof. And a direct proof works as follows. We start with what we know, we argue logically, and we end up with what we're trying to show. So in a direct proof, we always assume that the first statement is true, and we argue from there. So example, prove that if n is odd, then n squared is odd. Alright, so let's do a proof. The first thing we're going to state is n is odd. How do we know that? That's a hypothesis. That's given to us. Right? We're trying to prove that if n is odd, then n squared is odd. So we're going to start off and say, okay, let's suppose n is odd. Argue, and eventually come up to the conclusion n squared is odd, in which case we'll have proven this statement. So we start off with n is odd, that's given. Well, really the only thing we can do at this point is write something based on the fact that n is odd. And here's something we can write. There exists a k, which is an integer, such that n equals 2k plus 1. This is the definition of the term odd. Okay, well, if there exists a k such that n equals 2k plus 1, then there exists a k such that n squared equals 4k squared plus 4k plus 1. And that's just algebra. I said that since n is equal to this, n squared is equal to just this thing squared. So 4k squared plus 4k plus 1. Well, this means we can write n squared is equal to, and it almost looks like an odd number. It's something plus 1. Right? To show that n squared is odd, we need to show that it's equal to 2 times some integer plus 1. Hey, guess what? 4k squared plus 4k is twice 2k squared plus 2k plus 1. So that's more algebra. And then 2k squared plus 2k is an integer. Okay, and that's just properties of integers. And so we know that there exists some j, which is an integer, namely this thing, such that n squared equals 2 times j plus 1. And I could have used k, but I'm switching to a different k because I don't expect this to be the same as this k up here. So since this thing is an integer and n squared is twice this thing plus 1, I'm just rewriting that as saying there exists an integer such that n squared equals 2 times that integer plus 1. And that's, I don't know, I'll just say algebra. And then the punchline is n squared is odd, and that's the definition of odd. Because the definition of n squared is odd is saying there exists an integer such that n squared is twice that integer plus 1, and that's exactly what we were asked to demonstrate. So there's a proof that if n is odd, then n squared is odd. And it's a direct proof because we started with what we were going to assume was true and argued until we proved the thing that we were trying to show. Okay, there's another method of proof that we'll use sometimes, and that's an indirect proof. So how does an indirect proof work? Well, as follows. Let's prove that if 3n plus 2 is odd, then n is odd. Well, a direct proof would be the following. This is a direct proof. We'd say 3n plus 2 is odd. And that would be, what we're given. And then we'd say 3n plus 2 equals 2k plus 1. So that's the definition of odd. And we might do some algebra and say 3n is equal to 2k minus 1. And from that we might conclude that 3n is odd. Right? And it's not clear how to get from any of this to the conclusion that n itself is odd. So you can do it, but it doesn't really sort of like jump to mind how to do this. So we can take a very different approach. So what we're going to do is assume n is even. Okay, and this is an assumption. Then we're going to say n equals 2 times k, and I'm being abbreviative here. I'm not saying there exists a k in z such that, but we can write n as 2k. That's definition of even. And now I'm going to write 3n plus 2 equals 3 times 2k plus 2 equals 6k plus 2. That's algebra. And then I'm going to write 3n plus 2 equals 2 times 3k plus 1, where 3k plus 1 is an integer, and that's more algebra. And then I'm going to write 3n plus 2 is even, because it can be written as twice an integer. That's the definition of even. And so what have we done? We assumed that n was even, and we showed that 3n plus 2 is even. But we're told that 3n plus 2 is odd. And since 3n plus 2 is odd, n cannot be even. Because if it is, 3n plus 2 would be even. So this statement must be incorrect. So the statement that n is even must be false. Not n is even must be true. And if n is not even, n must be odd. Which is what we were asked to prove. So indirect proofs feel a little weird sometimes, but what's really going on here is contrapositive, right? So let P be the proposition 3n plus 2 is odd, and let Q be the proposition n is odd. And we're asked to prove that P implies Q. Well, what did we prove? We proved that if we negate the conclusion, if we start off with not Q, we end up with a negation of the hypothesis. We showed that P was false. Well, if not Q implies not P, then P must imply Q. That's the contrapositive. And so it's one step from the result of this indirect proof to showing what we were actually trying to show, which is if 3n plus 2 is odd, n is odd. So that's an indirect proof, and it's different from a direct proof. We usually start off by negating the conclusion and then arguing to a contradiction. Okay, and once we do that, we know that our original assumption must have been incorrect. But it's really just a direct proof of the contrapositive. So we can prove all kinds of things like this. For example, prove if n equals a times b, then a is less than or equal to the square root of n, or b is less than or equal to the square root of n. Well, how do we prove this? Let P be the proposition n equals a times b. Let Q be the proposition a is less than or equal to square root of n. Let R be the proposition b is less than or equal to the square root of n. So we want to prove that P implies Q or R. Well, let me show you the sort of hand-wavy way to do this indirectly, and then we'll see why it actually works using contrapositive. So, let P be the proposition n equals a times b. We're going to assume that's true and then show that one of these things must be true. Well, let's flip this around. Let's suppose a is bigger than square root n and b is bigger than the square root of n. So suppose that this or statement is not true. This is false and this is false. So a is bigger than root n, b is bigger than root n. Then a times b is bigger than root n times root n. And square root of n times square root of n is equal to n. So ab is bigger than n, therefore ab is not equal to n, and that contradicts our original hypothesis. So having reached a contradiction, we know that this thing we supposed must be incorrect, which means that one of these, at least, must be less than or equal to square root of n, either that or that. What we've really done, though, is we've said, okay, we want to prove P implies not Q. Let's look at the contrapositive. If P implies this, then the negation of Q or R implies the negation of P. And De Morgan's theorem tells us the negation of Q or R is the same as the negation of Q and the negation of R. So we started off with negation of Q and negation of R, and we argued and we eventually got to the negation of P. So we proved that this was true, and by contrapositive that therefore proves that this is true. So there's a tension here, right, between the logical part of our mind that already kind of understands these things and the kind of analytical part that's trying to put it into this very formal framework. And it can feel frustrating at first to try to reconcile these two things, but the more you work through these things and play around with them, right, change them into this formal language or use this informal language of English, the more you play around with those and try to connect them, the more it's going to make sense why these things are equivalent and why this set of techniques of doing the proof through logical reasoning actually makes sense. All right, so we'll come back in the next video and I'll show you one final proof, and this is a very old proof that the Greeks discovered thousands of years ago.